Questions? Why not start out that way?
So I have one comment to Roman's talk is that, this whole feedback loop was used in the field for a long time. Of course, not with artificial intelligence, which are graduate student intelligence. It went quite well.
Call it artificial.
That's artificial.
Neural network, and then there's artificial neural network.
So for quantum reactors,
So what many people in our group was doing really forever, and other groups as well, it's not specific to us.
but
Is
for
that,
what kind of system?
any system, like
I mean, systematically.
water dimer, for example, or argon HF. So what you would do, you would do exactly as you said, generate a very low quality potential based on few points, fit it, calculate some observables. So we usually calculated Villiers coefficient because very accurate data are available, and did some molecular dynamics, and then we would basically make some sensitivity analysis, and then add new points in the places which we thought were important. Of course, as I said, it was all based on subjective decision, but that was the only way of going sensible ways through the space, configurational space, because otherwise you would get kind of enormous numbers of points. Now people can use enormous amounts of points, but at that time it was impossible to calculate 100,000 points.
Joel?
So, a couple of points as well, I guess. So how do we generate our data? We generate something between 10,000 and as much as 200,000 points. So how do we select it? It's a good question, and so indeed, we never use uniform grids, because as Roman said, if you did 10 points per degree of freedom for a 4-atom system, that's already 1 million points on a direct product grid, so that's out of the question. In the end, we wind up with something like per degree of freedom 2 points, if you want to think about the multiplication. So, simplest thing, one of the simplest things is to run low-level classical MD on the fly. All right, and you start the trajectories at various places on the potential surface, really widely separated. So this saddle point, that minimum, this isomer, that isomer, these reactants, those products. You just start running swarms of trajectories, and interestingly, if you run them at different energies, of course, they
Just simple classical.
yeah, just classical.
Okay.
And what happens is you run them you have to run, let's say, fixed energy. But what you see is the distribution of the potential values is Gaussian, as it always is. It's amazing. And so your potential values will vary from something very small to something like half the total energy by a virial. Okay, so this can generate 1 million configurations for you in no time, using some low-level DFT. All right, so then you need some technique to sift those 1 million down to something like 10,000. Again, it takes about 30 seconds to figure that one out. You don't want trajectories in phase space that are virtually identical, because these trajectories, they just move along like little ants. Here, femtosecond. So you definitely going to throw away every 100th point, or something. So you've pruned it. What you have in this first iteration then is data that's really very widely scattered.
So it's global.
It's global.
Just like he gets.
Anyhow, it's global, and you don't know where the heck it is necessarily. All right, so then you do your first fit, and the way we do fitting, it's linearly squares fitting. The cost for our fitting is virtually independent of the data size. This isn't true, as Roman knows, for the Gaussian process. The training is an n squared n cubed procedure, so you really want to be down there with a very small data set. The way we do the fitting, it's virtually independent of the data size. So we can take 10,000 points. All right, fine. Then, many different techniques. These go back years and years, and we can put it in the literature. Now we go search for stationary points. Once you have a zero water surface, and if it's pretty rugged, and we like to work on those because those are the most challenging, you're going to look for all the stationary points on your zero order, your first pass. You find hundreds. I don't know. You'll find a lot. Okay, so that's already, your machine can do that. Your machine learning does that, and it says to you, I need more points probably. Where I've got local minima, where I've got saddle points. Fine, you add some there. And also, I'll shut up. So, in other words, there are, techniques out there, and everybody who does surface fitting has their own, and has developed them over time, and that's great. The one thing I did want to say about this feedback loop, and ask Roman. So, you mentioned sort of like 3 steps: generating the electronic energies, doing the fit, calculating the observable, and then looping back. Now, calculating the observable can be the rate limiting step, depending. All right. So, if we want to do this for, say, diatom reactive cross sections, exactly calculated, this means taking, let's remember yesterday's talks, how long does it take to run a convert couple channel calculation for, H2 plus CO? Hour, 2 hours, a week, 2 weeks, whatever it takes. So, now you're sitting with a potential surface that's not nearly converged 3 weeks at a supercomputer, whereas I'm calculating 50,000 points a day, or maybe not 50, 10,000 points, or 1,000 points a day on my local cluster, which has 50 nodes, and I'm running MolPro. Right? I think you get my point. I can run many, many points while you're doing the couple channel scattering calculation on the first generation.
Run many points. You run many points to calculate points on the surface.
Yeah, I can calculate points on the potential surface, say for H2 plus CO, many times faster than it's going to take you to do the converged, not J equals 0, the converged cross section. Maybe somebody's measuring.
Unless you have, I'm dumb on this, but unless you have a way to help you by machine learning or some other hook or crook, reduce the number of channels as well.
Well, that's a research topic, and that's fine. All my point is this: where's the bottleneck in this loop? And if it happens to be where you calculate the observable, and if it's a significant bottleneck, Roman, what's the answer?
It's a very interesting point I'd like to make. Well, first of all, everything you're saying involves graduate students. And I want to exclude graduate students.
Hey, if you can find someone to do this work for less money,
I know.
let me know.
But I guess the main reason we're doing this is because what we're aiming at the end of the day, is a surface that, when plugged in the dynamical calculation, gives an exact match with the observables. Like we have an experimental set of data, and we want to reproduce them exactly. So this is why we're doing this. So your calculations will not produce the exact match.
Why not?
Because they're going to be subject to errors of your potential surface. It's always going to be there.
There's our two.
But no, the way I construct them, by construction, they're going to give you the exact match because I construct them by the feedback loop. But let me also address the point about the quantum dynamics being the right limiting step. It is true, but we could also use approximate techniques there. And what you will get at the end of the day is a surface. It's going to be an approximate surface, a surface with errors, but the errors of that surface will cancel the errors of the dynamical calculation. It goes back to what you were saying.
No, I would never advocate that. Please don't.
Well, why not? All you want to, at the end of the day, you want to have a method that can be used to describe your physical process, right?
No, not me. Don't ever sign me on to that, please.
Well, say you have measurements of total cross section, so you want to.
Is this predictive?
Well,
because you want a method that's predictive, passes through what's already known.
Right. Yeah, absolutely. So what you want is to train the method, for example, on the total probabilities, and then look at the state result probabilities. And it remains to be seen if this can be done, but I believe it can be done.
Free lunch, Roman.
To some extent, you're trying to solve the inverse scattering problem.
It is.
Which is a totally different problem than what he's talking about.
Right. It is.
What's that?
Right.
You're solving
I'm
the
trying to
inverse
solve the
scattering
scattering
problem,
Yeah, exactly.
which is different from what Joel wants to do.
In essence.
So I don't know why we're having this argument.
But I think you are also getting
It's a
right
condition
result for
problem.
wrong reason. If you use your surface is not good. It's good only for this problem. If you use it for other problems, it will be really
Sure, I will use the
could be
other.
disastrous. And
I don't want to have a general method because I have a machine that can adjust itself to any particular problem, right?
no, but we, for example, produce a surface and we calculate various properties: scattering cross sections, spectra of advanced molecules, and properties of condensed phase. So if we fit it on only one set, probably the other properties will not come out.
But isn't that interesting? I mean, I think this is cool because it's almost like it's, I mean, I guess because it's the inverse scattering problem. It's like,
It is.
well, what's the most important thing to get the total cross-section? Well, it looks like this, but if I'm looking at, collision-induced absorption, it's going to look like that. And to me, that's telling you something about the
Yeah,
physics.
exactly.
If there is a difference, then you're going to get some information about the physics of those processes. But I'm,
So that means like, you are fitting to a reaction probability which may be for total J equals 0 or something, and so that means you will have to fit each state-to-state reaction probability. You need to come up with a new surface, and if it is a state-to-state cross sections. So how is this?
I hope not.
But can you guarantee that your surface that fits to the total J equals 0 reaction probability would also yield all the state-to-state reaction probabilities with the same accuracy, or you need a separate surface for each state-to-state?
Well, I can only say that in the calculations we've done so far, we always get the surface that's as good as the full surface that people calculate through traditional methods, right? Which implies that the surfaces we obtain can be used with in the same way as the other surfaces. But it remains to be seen that this can be done for systems like Joel's, right? Because there, I believe we will run into the problem where the results are not unique, and then you may have multiple surfaces giving the same result, and then but this is an interesting research topic in my opinion.
Do we fundamentally believe, by whatever method we use, that if we do it, we sample properly, that we will get the right answer? It's just a matter of how we do the sampling, and you want to find the most efficient approach to do it, both from an intellectual and a computational point of view.
Let me go back to a simple four-atom system. Formaldehyde, H2CO. It has a deep minimum, and there's been a lot of work done to get the potential surface really accurately done around that minimum. It's spectroscopically accurate. Walter Thiel has just put up. He's probably got the most accurate surface.
Okay.
Done. And it is a monomial expansion in internal coordinates. Jonathan will correct me immediately if I say anything wrong. And it was an extremely precise fit to a small number of ab initio points, and the spectroscopy is probably the best in the world now.
Okay.
Now, there are high energy isomers of formaldehyde. The hydroxycarbene got kind of interested. They've been observed experimentally. They're up about, if I can use wave numbers, about 18,000 wave numbers. There's a cis and trans hydroxycarbene isomers. Well, his surface is useless, obviously.
Yeah.
Totally garbage.
Because he did it locally.
It's local.
Yeah.
But he selected the points appropriately for that local fit, and it's now the most spectroscopically accurate surface, provided you don't go very high.
So
But now you say,
in that regard, so what
What do I
happens
do?
with these methods?
Yeah. Go ahead.
I'm thinking, in my mind, of course, immediately came my former postdoctoral advisor, Howard Taylor, who
Yeah.
worked on a lot of these things where you have both chaotic and non-chaotic behavior, in some of these reactions. I mean, what happens to all these methods when you get into those regimes? Maybe that's the regime you're talking about.
It is, because you know what, this is kind of where I see the frontiers of science going. I mean, why do we want to refit the minimum of formaldehyde again?
We don't. That's why we want to use this to focus on the high energy.
Well, we just wrote a paper where we applied this approach, and thanks to Roman, we have the GP method, his code, and we did apply it to the hydroxycarbene problem. And I would say it works. It works. It's not as, we could never do it with 30 points, I can guarantee you. There's no way we can do the formaldehyde, the cis and trans hydroxycarbene, and the barriers in between Forget about the reaction products. We aren't even thinking about H plus formal or H2 plus CO. That's too hard. And it took a few points, all right, and we looked at how many points it needed to get this thing reasonably well fit.
Okay.
And well, the paper just got reviewed. It was,
No, but I mean, did you conclude that it helped?
I concluded this was not magic. I hate to say
Well,
this.
Well, nobody's saying it's magic.
But it sounds like it.
You know, we did from other items as well, right?
You did the global minimum.
Yeah, we did.
And,
we did the-
and Walter Seal did it with old technology, and it's spectacular.
I know, but
So
we
there's
did-
no point, I think, in, doing what, let's go somewhere where, those old methods from the 80s and 90s just are gonna fail. And we need really new ideas. And that's an example.
Oh, absolutely. But
And
it's
as
a
I said, so
starting
we
point.
did it. We did it. It's going to come out in JCTC soon. Well, we did it with another method, our old method to do fitting, which they're about a wash.
But I mean,
They're
you
about a
had never
wash.
done it with your method before?
Yes, we did. We published it, of course, not long ago.
So what did you learn when you compared what you had done then and now?
I'll tell you one bottom line. So the
That's
method GP gets very slow if you need 500 or 600 points to train.
5,000. You mean,
Oh, it gets really slow with 5,000.
500 is
All right, so even with 500, it's in the paper, and I'll show you. The other thing is the time to evaluate. So when you evaluate the potential, and we finally put timings in this paper, and the two reviewers, I think, sucked it up and said, okay, the timings are there. It's slow. Of the three methods that I put up yesterday, permutation, fitting, neural net, and GP, on a same size data set, and even if it is like 1,000 points, GP is the slowest by far to evaluate. The reason is you're using all the data. We aren't using, anyway, it's a very different approach. So the timings, we're very much faster. Now things catch up with formic acid dimer, and I don't want to go through all the details, so we're trying to be really fair. So it's not cut and dried. It's not cut and dried. We just applied GP to a 45-dimensional problem, which is by far a world's record, and Roman wasn't sure that was going to work. It did, and it's much to the credit of your code and GP. It works. It's pretty slow, but so is our method, and for a variety of reasons.
Okay.
So all I say is, I don't want to get to this point where we're sort of fighting with each other as opposing armies, and there's going to be one person standing. Let's not do that.
No, let's not do that.
Exactly.
Then we're going back in time instead of forward.
Right. So let's move this field together, and acknowledge each other's, we can do certain things well with this approach, we can do other things, well with that approach, and it really isn't going to be one person, one approach standing at the end, and the rest is just dead bodies.
But I will add the additional comment that if we work together, then we can make all these approaches work optimally
Absolutely.
for other people as well as ourselves.
Absolutely.
And I think, Armin's talk to me was really great because, I see how hard he worked on, doing this very nice structuring of things. Now, whether it's C++ or object-oriented formatting, I don't care about that. But the fact of the matter is that what Armin is saying, I think, I'll let him say it himself, that he really, in the long run, got something that paid off out of that.
I tried to convince myself of that. No, I think it does. It's moving. One thing I forgot during my presentation is I'm using this to let bachelor students go into the code and program. That has one thing. It's a nice training. I tell them this will be a bachelor work where you're doing real computing if you want. It requires they know programming. Yeah. The other effect is foolproofness. There's no greater source of fools as bachelor students.
No, it's unfair. But it's this resource. You're very embarrassed as a professor who has this beautiful code, and the student runs into something, and it's a trap, and it's a trap. Yeah, so that helps to promote the code. So in that again there, and I have noticed in the implementation of new features after the structure was there, that it's getting really fast. I can do things, quickly put them in, putting those blocks in a relatively complex situation with multidimensional, adding another layer, adding another dimension, coupling stuff, stuff like multi-channel. This is all the same scheme, and you can permute things, and I mean maybe so. You can say, for example, this is all tensor type of structures. The Hilbert spaces are tensor spaces. We can factorize them. We can then work on the products, and not without them being factors to begin with. So we have to disentangle this hierarchy. All of this can be done, and that is a very useful tool. Say we need a projector which is actually from a tensor product space, and we can very efficiently apply it by decomposing it into its tensor factors and stuff like that. So we can now remove much more on a mathematical than on a programming level, and in that sense it paid off. So we're doing really complicated stuff.
And I would say that, in my view, from what I learned when I was in OCI, looking at other areas of physics, you find that these kinds of things are being done. You take like the cactus code, which is a code that's used in the relativistic, black hole binary collision community. I mean, it's the same kind of idea that you have a structure and you can do many things. You can, code the PD, you write the PDE out and it takes care of the discretization and all of this kind of stuff. So,
I'd like to comment or have a question for Armin in connection with the statement that the students should have a little bit of experience or should be taught a bit about software development. So I would totally, software engineering. I would totally agree with that. The question is a little bit to what degree is such an effort already implemented at universities, and to what degree can one actually squeeze it in? I talked to Fernando yesterday and pointed out that, for example, in Hamburg, after the Bologna reform in Europe, there's not even space for anything like scattering theory in normal quantum mechanical training. We don't do it, right? And it's also because the condensed matter people don't care about it. The type of scattering theory that the high-energy physicists need is let's say, less severe, right? So often simpler, and they do it in quantum field theory. So it's all the quantum mechanical scattering theory is not done. We even put together classical mechanics and classical electrodynamics into a single classical field theory course in order to compactify. What I'm trying to say is that in a lot of undergraduate training that we do, the focus tends to be mostly on analytical skills, which is what the string people and so forth tend to want, and within physics that tends to dominate a little bit, right? The mathematical physicists, the condensed matter people, and then there is little room left, I'm afraid, to actually properly bring that in. As you say, they don't need to be software engineers, but still there needs to be a forum, there needs to be a place where they can actually do these things, and and there are a lot of students that are produced in Hamburg, but not only in Hamburg, that often don't know how to program, but they really know certain mathematical things really, really well. So everything has to be postponed until they start a thesis, and then they have to learn all these things. That's a bit the situation we seem to have at the moment. So that's not always the students coming and, they have all the skills to begin with. Often they have to be trained later, and I think it's too late. So I would actually advocate that we should try to fight for that.
Okay. I'll get you with okay. You go ahead and then Lincoln.
Okay. I don't think we should squeeze everybody through this kind of software engineering thing. We have, at least at LMU, we have basic programming. People coming out of that know very little about programming, and it's taught by us, and still it doesn't work really yet. Something like this code is a training tool because it has a lot of good examples, hopefully, partially. Some of them are bad. Yeah? But my first problem was I had to become aware of it, not to say to learn. I had to become aware of it myself. such that with some security I could tell the bachelor student, no, you don't do this. If I can argue with you now for 5 words, if you want more, I just say no, do it. Because they don't understand the implications until they have seen the far end. Yeah? So I think for me it was certainly such that I had to learn it myself first. And then I'm doing sometimes, anyway, I have to do computational physics, and I try to kind of communicate these principles. I think it cannot be much more. Really, to learn, you learn it when you work in a certain level of complexity. Before that, it's dangerous, it's silly, and even dangerous games. These kind of things of, oh, we need to build this and that structure. You have to understand why, otherwise it's... So I don't say it should be a fixed part of the curriculum, but it should be part of our attitude. Us doing a lot of computing, so it's mandatory, and we should try to communicate.
Do you want to follow on?
Sorry,
Wigan wanted to say something.
In Belfast, what we're now doing is, well, no, we are fortunate that the UK Parallel Computing Centre puts on good training courses for PhD students to basically look at things like proper software engineering, proper maintenance of large-scale codes, also all kinds of training courses on parallel programming skills. But we're now getting more and more into sending students onto a training course really to look at software engineering and the basic principles of software engineering, version control, etc. Because it really is absolutely critical to student training.
But it's a little bit late, is my point,
But
because
it's
it's
probably-
actually the experimental community that is sending.
It's probably
Let me,
at the right phase.
go ahead, you comment on one.
Of course, this is an international audience, but regarding what's happening in the U.S., I have been working on this myself personally. I think I'm the only person in a large university doing this, actually. So you may be aware that American Physical Society and American Association of Physics Teachers, which is our educational organization, issued a joint recommendation that all physics programs should integrate computation across the curriculum, actually. And that's changing now. So some smaller universities with small programs, 10, 20 majors, prototype that. Now mine's doing this at 300 majors. And I think there's no question that this is needed. And why do we know it's needed? Because most people who get an undergraduate physics degree don't actually become us, right?
Right.
And the number one skill that they say they need on exit interviews, because we know because we interview all of our exiting seniors, is computation. That is the number one skill they need. So if we're going to be good educators, we have to do this anyway.
Yep.
That doesn't stop us from becoming, people working with analytical methods or physics professors. Actually, that will not slow down the physics professors. It will just give them more tools. But I just want to mention that because it is a nationwide thing that's going to happen in the U.S. So about 10 years from now, the whole country will have students with those skills anyway.
There's a difference between computation and large-scale software engineering for large-scale.
Totally. But as far as basic competency,
Sure.
most big cities don't have that because we don't give it to them. So I just want to mention that's happening.
So Australian approach to it. So one of the joys of being a departmental chair is I get to decide what our program is. So in first year, all of our physics students will take object-oriented program design from computer science. They will take Unix and C from computer science. They will take data structures and algorithms from computer science. They will also take accelerated mathematics 1 and 2, and I say the real physics begins in second year. The reason being is we need to have their skill set in computing to feel very comfortable to use with computers generally, and have the mathematics level already at the university level past school. Only then real physics can begin. So we can't teach as breadth of physics as a consequence, but our students, for the very reason Lincoln just articulated, many of them will go into other things, other science areas, and mathematics and computing are just critical foundational skills, and it would be it'd be very wrong for us not to give more physics at the expense of those skills. And for us it's working beautifully because we know our top students go on and are very, very successful, even though they might have done less physics. That part they can catch up on. If they've got the mathematics and the computer literacy, no problem.
Is this being taped? Are these two statements also being taped? Very good, very good, excellent. I need to have this at home.
Why is that? To tell your administrators.
Correct.
So it sounds like the two of us have both been involved in large efforts. So if I can say this, anybody can contact us if you want details. I mean, you must have proposals to motivate your faculty. We have years of critical mass to get to the point where a whole faculty are willing to do this. So,
Jeppe, you want to say something?
No, I agree completely. Of course, it's important to distinguish between the computational physics and the software. And even software, we see that a number of one day they learn to do a bit of Python, excellent, marvelous creativity, but the thing of getting down, programming with C++ or Fortran, that is really a minority, and that is getting thinner and thinner in many places.
So it is my experience, for example, that I have had students, undergraduate and graduate, for a couple of years, and before they didn't know anything about revision control, about makefile, about compilation, about more than one single file for code. They have learned how to write simple programs and manipulation of data after all. They wouldn't be able to contribute to real advancement of the code. I have to do that myself, maybe sometimes with the help of a postdoc, and towards the end of the PhD, one of them at least should be able to write a sparse version of the TDSC solver, starting from a set of codes that we have developed as examples. So what I can see is that for the way they are prepared at our university, they don't get the background to do advanced programming, but they can see how best practices are implemented and learn by example. So I believe that most of my students will take from the internship with me the ability of being aware that there is the need of coding well in order to get things working.
I would argue in the early days of computing, pre even me, I mean, it was physics people leading the way, right? And so why not keep the tradition, lead the way? If you need to educate these students and it's not being done, and I understand that it's not being done in a lot of computer science departments, then it has to be done somewhere else. So we should take that. We should make the physics people or the chemistry people, or just make them have to take what they need to learn this class.
I would like to make a statement which somehow counters what I said before. You throw this bachelor, for the bachelor thesis, you throw that poor guy into the code. There will be a small subset who are able to do this. And then you will get crap and good results. And you throw away the crap, you keep the good results. Very simple. But the computing part, when there are structures that people are able to understand, the computing part for somebody who has mathematical training is very quick to pick up. I don't think if there are examples that if there is people who are good and who are able to abstract in general, as it is trained in mathematics, they will pick this up from seeing a good code. It's not, but of course to build a big code from nothing, you need to think more general. So, but I think we can do much of that. Of course, it's nice to have this training, but thinking of what happens in Munich, if you come along with an idea, like wasting 1 year on this stuff, you will be killed by 3 people. Yeah. It's over.
So I have to say that I'm listening to Armin, and it looks like a fairy tale, and I would wish that something could happen. Maybe if Lincoln is right, maybe it will happen, but I have been fighting at the University of Delaware for like 10 years to introduce decent computer science courses for science majors. And it doesn't work at all. I mean, we cannot teach it because there's this, at US universities there's this, computer science teaches computer science, physics teaches physics. So they have to teach it. And they teach 2 types of courses. One is really like, I would say, how to use Windows 10. That's really this language.
How do you use Windows what?
Windows 10.
Oh, yeah, right. They should give a course on how not to use Windows.
And the other ones are courses really completely, they talk about theory of parallel programming, about some, beautiful things and proofs, but I love the stuff. It's not what our students need. They completely use it. They finish this course and they don't know how to write simple programs.
Go ahead.
I'm glad that we're on this sidetrack because we all have a lot to say. Let me just, about my university. So we have something called the Institute for Quantitative Theory and Methods at every university for our undergraduates. Sounds cool. The people who teach this are mainly from the political science department, and biostatistics, political science, all right, math and computer science, that's good. More political science, economics, etc. It's got a lot of money, and a lot of students take it. I will go through it's in its infancy, maybe 3 or 4 years, and R is one of the major codes they use. Some of you know what that is, some of you don't. But obviously, that's happening completely independent of the sciences and to some extent even the math department. So, and who is it? Who's the audience?
Who drove it?
Well, our dean, it turns out. Our dean did it.
Without any input from people?
Nope. It was one of his, well, I think, the deans they talk to each other a lot. So if something
But not to everybody else.
If something new is happening at your university, the chances are it's happening a lot of places. These deans meet and conspire, and then they think, oh, this is what we should be doing. Anyway, this is a huge program. Lots of undergraduates are taking it. And we're starting to think in chemistry that we should be having our students take their courses instead of the conventional math CS courses for prerequisites for, say, physical chemistry.
If the courses don't fit.
No, they do. It turns out they're doing a great job.
Oh, that's good.
With this stuff. It's a different perspective. As I said, they use R. And so do they use Python? I don't know. But, they're out in this other world. And a lot of it is, by the way, GP is in there, as you know. A lot of it is statistical. So a lot of it's statistics. So a lot of our students, maybe they need to learn statistics or when they go off. Less so, ODEs. So the data analysis, a lot of times that our students are doing when they leave the university, may not be quite the things we traditionally teach them. But it is a lot about how to handle big data. And so in a sense, they're now getting these courses to do that.
Well, I guess just talking about resources, and there's a class at Harvard that's one of the massively online MOOCs. I think it's called CS50, but it's a basic computer science class, and it's free as far as I know. Unless you want to grade, then I think you have to pay money for it. But they run it all the time.
You and 500,000 students.
Yeah, I mean, and the thing is that the stuff that we're talking about is stuff that, I know about the class because my daughter, who is a straight biochem major, took this class her sophomore year and became a computer scientist. So it's accessible to someone who's got, who has math and a little bit of physics, but is a chemistry major, and they learn these things all these things that we're talking about. And it's something that they can do. And what's happening, and this is, I guess, it's your number, is that the students are taking it because it's, they think it's going to improve their resume, I guess, or something. And so it's a resource that's out there.
Hussein, do you want to say something?
Who teaches it? It's in CS?
It's in CS.
Computer science department. There's actually in class as well as the online.
Yeah.
So in fact, just yesterday there was an op-ed in Wall Street Journal written by one of the Silicon Valley technocrats, which the title of this op-ed is "Stop Teaching Calculus, Teach Them R."
That cuts against
I think we will follow fast.
Stupid. You don't say that. I mean, you're teaching calculus and you're teaching all. It's not.
No, I mean, this was to make a point.
What?
Well, you need to know calculus to use R.
Yeah. Well, maybe. But I think if you learn maybe you'll argue with this, but I think if you teach students well with one good programming language, whether it's C, Fortran, or C++, if they need to learn another one, it becomes a hell of a lot easier once they know one.
For sure.
And that's where we're not giving them even one, right?
Yeah.
And then, if you basically have a program that's set up well, then actually also the development can go a lot faster because everything is set up in an easy to understand way so the students can pick it up easily.
Yeah.
Well, maybe we should, it's a little early, but maybe we should, if there's anybody else who has any, just a couple, because we have to be out of here by 12, so a couple more. And then,
By 11.
Oh, I meant 11. By 11.
11:30.
No, 11:30. Oh, so we're okay. I apologize. Go ahead.
So let me comment on the calculus. I'm of course not advocating removing calculus from science education, but, and again I realize here that the American system is a little bit different, but we for example have mandatory functional analysis, Banach spaces and all that stuff in our undergraduate math training. And I can see that for some people this can be very useful, but I really am convinced that for the vast majority of physics students, once they graduate, they will not do anything where they will ever be able to use or remember much of it, and they lack all the computational skills. So I still would very strongly say this trend that's already starting in the US, and I think we're in Europe, at least in Germany, we're not really following that trend in any consistent way. We should learn from this. And what you're describing, what you're doing in Australia, that makes a lot of sense to me. And most students would profit from it. And we tend to overdo it sometimes in the math areas. In areas which, for example, our community certainly wouldn't use. It's very advanced stuff, and I'm not saying it's not interesting. What I'm saying is there should be the opportunity to take it if one goes in that direction, but that should not be the mandatory things to be
I don't know whether, sorry, are you teaching math against computing? So
I have to because we have a limited amount of curriculum.
My best students are those that are really good in math. That is what matters.
You see, it's interesting. I received both as a student 30 years ago.
Sure.
Right?
Yeah.
So somehow it was possible then. It certainly is still possible. One of the things I like to ask people when I'm traveling is how their university is organized, because everybody does things just a little bit differently. And I sense that, certainly in the United States, in the Bologna model, there's a lot of general courses. So there's an emphasis on breadth that, of course, cuts into it.
Yes.
Right? Well, that's you're saying in physics. And I talk of our degree as a multicultural degree of the culture of computer science, the culture of mathematics, and the culture of physics. Now, for me, that's three different cultures, right? But for others, it's all one, STEM. STEM, that's an acronym that's used regularly. Yeah. Right? So it's just one thing, and there's a real push to get away from so much technical stuff, and to push, and that's what I have to fight. But it sounds like you have a bigger issue. But are you saying you're having a lot of physics courses? Is that what you're saying?
No, I mean, we require physics very broadly. Everyone has to take not only, basic introductory physics courses, but everyone has to take solid state, everyone has to take particle physics, everyone takes this stuff. And I'm actually in favor of broad physics education, but that's what uses up much of the space, and then there is a very deep math education. So Armin is very much in favor of the math training, and I understand that. I agree the ones that are good there are doing well, but we are in a system where it's the norm that 50% of the students drop out, right? Because for various reasons, but that's one of the reasons. And at the end of the day, most of them won't be working in the very math-oriented fields, and a lot of them will require computer skills that we don't offer them.
All of them will require computer skills.
Yeah, absolutely. The vast majority, if not all.
We can have this system-specific discussions, which I think certainly has merit, but I think at the end, I think the trend of this discussion would be that whether you want to have the person, the trained person, whether undergraduate, graduate, postdoc, or faculty, you can do an integral by hand or use quadrature.
Or call that, or ask mathematics.
Well, mathematical would be somewhere in between.
You could do anything.
This is what you would want to.
I mean, I think you want,
So I'd like to try to turn the discussion back to the purpose of the meeting.
Yeah.
Because I think this is all valuable and interesting, but there's all kinds of tools, right? Calculus is a tool, statistics is a tool, algorithms are tools, right? There's all kinds of tools, but somehow I have trouble equating Klaus's code with calculus, right? I mean, these are very different kinds of tools, and putting them in the same bin seems a little bit counterproductive at this point. So we all would like students who have access to lots of tools. We'd all like them to know how to use the tools, and we all have to invest in their education to make sure that that happens at some level. But can we talk a little bit more about Klaus's tool, or some of the more advanced tools that we've heard about here, and what you would like to see and what you would like to get out of this workshop in terms of those more advanced tools? That's sort of where I'd like to see the discussion go before we wrap up today.
Let me get back to Roman and say nice things. So I do think we have a variety of very different approaches to fit potential surfaces. And GP is definitely, I like it. It's got some. What if we had an effort to get these techniques sort of bundled together in user-friendly ways? This isn't, easy or cheap to do, but there are, and the field's moving quickly too. So maybe it's too early, but there's something that's kind of ready, and it's fairly new, but it's already pretty well developed. A toolbox of these methods, and maybe you can run them all.
Right, Fernando and Armin and Luca and I actually seriously gotten, we just started a discussion, but it seems clear to us as a whole that we have lots and lots of things that we're all interested in, and it would be nice if we got together and we could have a collaborative call it if you want, where we could take the things that we're working on and put together something that would be a tool, if you want to use that word, set of codes, which would interplay with each other. People could use them, we could use them, we would all benefit from using them, and so would other people. And I think we're going to try to do that.
Let's propose an action item. Can I propose a workshop funded by ITAMP that would bring together not us, but graduate students with expertise of building those codes? It would come together with the purpose of actually building something like what Joel is proposing. Like they would come here for a month.
It would have to be long.
It would have to be a month, and then we would each send one representative, and that will result in an actual product.
What about the winter school? You guys still running the winter school?
Yes.
It doesn't have to be at this location, but what I'm saying is that would be a viable way of doing it, because if we could make it attractive to that graduate student somehow, I think that would work.
I'll have another thought. There's a Telluride school in Telluride, and I think they would be open to ideas like this too. I once approached Steve Berry about something like this, and he said, "Oh yeah," he wanted me to organize it. Well, I didn't get excited about that. So, but maybe that's a place where we could do something like this.
Maybe I can. We saw two beautiful examples where using some modern ideas from computer science can suddenly make a huge difference and improve the programs and how students can work with it. I think there is one thing we have not discussed much, I tried to address it in my talk, is graphical user interface. Because I think we all think about graphical user interfaces probably in the wrong way. We think of it as something that eventually our whatever software we write will be finished, and then we'll hire someone to make this beautiful interface, and then let the public play with it. But the graphical user interface, the core of it, as I discovered when I built these things, is extremely different from that. It has nothing to do about making the shiny box in the end. The graphical user interface is a JavaScript program that runs in a browser and that talks to your software, because it needs to give it some numbers and it needs to get something back. So once you build that graphical user interface, you will suddenly, your program will have gone from the Stone Age, where it was something living in a computer, to something that uses the internet, that knows about a socket, a TCP, that can communicate. And that means that if you build that graphical user interface, you suddenly have the ability to share your code with the world instantly while it is in the development phase, and you immediately benefit from sort of the documentation you get from defining that little protocol that you need for your program to talk to that web browser that will then communicate the few input parameters. We saw all this software as you wrote, with all these command line things. Well, what you have there to put the graphical user interface that will provide these few keywords, maybe an input file name and a few numbers, is in a way, compared to learning how to do object-oriented programming in C++, it is trivial. Once in your life you have to learn how to make a button, to resize a window, to pop up something, and to communicate. And then if you would do that effort, immediately your software would be available to the world, and also suddenly in your input you could add one little button that explains what that parameter means.
Absolutely.
Without having to start writing a documentation.
Absolutely.
It's two different communities.
Yeah. So I think there is big gains, and so far I don't think we don't do graphical user interface in our development phase. Right? It's something for quantum chemistry once you start to sell your program.
You need to make a YouTube video, seriously. We've done this, it's trivial. For running our software, it's out there, it's a video. Maybe not you, get somebody, I don't know, somebody with a nice sonorous voice, and have the bits, I'm serious, they're sitting in front of a computer screen, and we're watching them start from scratch to put a graphical user interface together. And put it on YouTube.
But this is already, there's many examples out there, many standard tools. I mean, just Google how to, it'll pop up. It's very, it's very easy. You don't, it just doesn't really require
I'd
us
much rather hear Jared do it.
But if I may, that is precisely the idea. So I don't want the student to have to bother about how many nodes the B-spline have, and to keep the knowledge of all the nitty-gritty detail all the time, because they have to know everything. The idea is to have a set of tools that are 20 command lines with the parameters that are documented. You print the name and you get a help list of what they need. And then the level of coding of the students is at the level of scripting, either in Bash or in Python or whatever it is. And they have this list of imperatives, like in Molka's scripts, right? Where you do calculations for close coupling, TDSC, scattering states, photoelectron distribution. That can be done. That is precisely the idea.
And it's good for even the more expert people. It makes them easier to do what they need to do. I mean, we're not talking about how you build the code, how you develop the code. That's going to be a small group of people, right? Typically. But we're talking. But even a user, even me, if I developed a good user-friendly piece of code, I mean, it would make it easy for me to use, not just the students.
So, for example, I have a student who is doing simulation in helium and now argon at the same effort to compute the control of decoherence in the density matrix of the parent ions that emerge from ionization. This is a topic that incidentally Robin has explored several years ago, and it was interesting. So you throw away an electron, and whatever remains behind is partly coherent. So you have to adapt whatever photoionization amplitude you get, or you trace out the electron states. And so the students just have to know that they have a system, gets ionized, it has photoelectron amplitudes on all the channels. How they are computed in the detail, they don't know. There is still a lot of physics that they can confront themselves with. There is some calculation with it, right? They have to build the density matrix. And that can be done at a much higher level and use the TDSC as a tool that they can launch.
But is your code published? Is it available?
Not yet. I hope it will be soon. But we have just the TDSC running since February, so it was quite an effort. And in fact, as you see, probably noticed as the programs went further and further, the number of options got longer and longer because they haven't converged yet to a minimum set. So I didn't have enough time to make them shorter.
And so what I am saying is that the step to make a graphical user interface and make your software available on the web for the world to play with it is less work than getting to this point where you feel comfortable of handing out your software with instruction on how to use it.
Absolutely.
So it's not something that comes after you've done all these things. I think it could be something that we do even before we get to giving out something with a version number, etc.
No, but I think if some collaborations emerge out of here and they mature, definitely they should result in having that as part of what.
If I may add one aspect, so there was the concern about using properly the structured code to get meaningful results and not doing iron like beryllium. Right? When you consider a general purpose atomic optimization code, essentially most of the time you're talking about neon and argon, full stop, right? Because the helium is done, and the other atoms are not easily accessible to experimentalists. So what is really important is to have a database of already computed well-converged structure for this energy region in this level of description of the correlation that you clearly say what it is. You make the matrices available. People can download those and run all the simulation that they want, and use something that is a code that you feel comfortable distributing and starts instead of from the description of the SCF orbitals, from the matrices, the close coupling matrices, and that is easily done.
I would like to add, I mean, we are talking now about a certain segment. This is users, but that's not the only problem. Our problem is to talk between us.
No, I said that.
And I think it's very, very important. So the graphical user interface, I think can be done easily, but it will be, this I would consider more a promotional tool, to be honest. Which is good, and once it is really matured, it's great. But what I find for the productivity of the community, I find it very important that we learn to systematically talk to each other, not in the sense of collaborations, but that's what quantum chemistry is different, it has a different history. But I think that's why, like Jeppes talked very well, we have to be able to agree on what we are doing by some tool. So I just wanted to not forget about all these beautiful possibilities of making things shiny. That's not the only problem. I'm trying to do this, as you have seen, and I see it as useful, but it's not the only problem.
No. But I was stressing, of course, that the interfacing part that you do, maybe for your graphical user interface, then also means that your computer programs can start talking to each other. And of course, databases are also very important, right? I mean, now if we need a rotational constant as input, you can go to a website and it pretty much looks like the scan of an appendix in an old book, Hertzberg in particular. For some weird reason, you cannot get a rotational constant through a URL. Like I showed the NIH, right, has this database of hundreds of molecules, so the pharmacologists already have that. These geometries of thousands of molecules are available, and you can import them with one line in your code.
So let me make a plug. So NIST has something called the Digital Library of Mathematical Functions, which is online. And every single equation in that online version has its own URL, and it will never change. And if you want to refer to it,
But is it what format? Because I looked at a lot of stuff of the NIST, and some of it is in, let's say, computer readable form. But just if you go to the atomic data, it's a table that a human can read very easily.
You're talking about two different things.
We're talking about
Aaron is referring to the database.
Yeah.
But I think Barry's referring is what he's been involved with, getting the mathematical Bible. On
Oh yeah,
on the
I think
internet.
I've seen that. That is a good development. Yeah.
Read
Yeah.
the February
Right.
Physics Today. We have an article on it.
Yeah. Yeah.
I have two things to answer Garrett. There's the NIST book, which returns data, right?
I looked
Equal constants and other
at
things.
quite a few
Yeah, it's
things
very
and,
limited.
and
Huh?
It's
certain,
very
well,
limited.
Yeah, but
There's also a lot of it is in graphical form, so
Yeah.
you can't really,
a lot of it.
they're like potential curves.
Yeah, but if you want rotation constants or other spectroscopic constants, they come in a table.
just play with it.
We scrape,
Yeah.
Quantimal scrapes in this
NIST
website for data.
Which one?
NIST, well, the chemistry
The
book.
Kimball.
The
Yeah.
Kimball book, yeah.
But-
It can be done.
It can be done, but a lot of stuff is in, not, all the formats are different and you can scrape, of course, but it's a lot of effort.
So
to get basic
let's try to
numbers
get
from.
back to the
Can I mean, we're talking again about screwdrivers and hammers, and I'm wondering about how the 20, I hate to keep using you as an example, Klaus, I hope it's okay, but I'm wondering about how the decades worth of work that Oleg put into developing these codes is going to be preserved, whether it should be preserved, whether other people should be able to use it. That's a little bit different than talking about screwdrivers, so I just
Well,
trying to get back.
Can I raise this now, Mike?
Sorry?
Can I raise now what we talked about?
Whatever you want.
Okay. At some point we're going to be having this discussion. I'm not quite sure when as to what we're going to get out of this. And I'm concerned some people may be leaving earlier in the afternoon.
That's fine, go ahead.
So I want to raise
We're
this.
winging it.
To my mind, it became sort of fairly clear how we can really make this workshop a big success. And there are many issues in getting programs going, and every hurdle has to be covered. Making source code available is relatively easy. Making users use it intelligently is more difficult. But there's other very major logistical aspect is implementing it on an architecture. So one of the things that I think possibly could come out of this is to have a supercomputer somewhere where a percentage of it is dedicated to people installing their codes. The positive sign for them is they get to use a proportion of that supercomputer with their codes. They can have it updated with something like subversion, keep conversions up there. They have access to it. They also guarantee that other people will have access to it. So on this supercomputer, people will be able to ask for an account to run this particular code. So we create a collection of codes that will therefore exist, like DBSI, and all of those things that already have been implemented. The make files are there. You can run them immediately and get your standard output.
But I think that doing it that way, and you can correct me if I'm wrong, and I'm not objecting to it, that's not a bad idea, and I would even know how we could do that. But I think that still would be something that would be used by experts, mostly experts.
And that's fine. But
I'm not objecting to that.
Nice interfaces into it, right? But that's a starting point, right? And people to know, look, we're going to lead. This is a place where the code not only resides as open source, but this is where it runs. And then if you want to move it to a new machine, well, that person can take responsibility.
I mean, we could certainly, I'm certainly sure we could approach the Exceed people and say we'd like to get a science gateway where we would be able to put these codes and that we'd get help in doing that, but again.
But that's the carrot for the other community. So if I want to see my codes used by others, then the carrot for me is I get to use a supercomputer to some finite allocation. If somebody wants to try it out, they also get some sort of finite allocation, but at least it runs. It's there. They can get the source code. It's a reasonable starting point.
Well, I'm looking for more than that. Anyway.
Sorry?
Wouldn't these cloud services, whether it's Amazon or Google cloud services, work as a repository and also as a platform where you can run these codes? Because those are being very heavily.
Yes, eventually, certainly. I'm just saying, what's going to be the starting point in making these things happen? You may go in that path and then you'll build the graphical interfaces. But we have to start somewhere.
Yeah, one of the things you can do is make the software available in a way that you, if you want to do big calculation, you just bring in from the cloud your own computer power, or maybe from your own computer center or your national supercomputer. So it's not so hard. Once you, so that is what exactly what I said. Once your program can talk to another program, then then you can easily do something like this. Have the big calculation run somewhere else. That is not a big step, but you have to start having the code, working code somewhere.
Yes.
And I think there's a big difference between having a source available and having it somewhere run.
Yes.
Because in practice, that is a big step to do that, right? There's a big threshold. It may take a day to download it, make it run on your own.
People don't know how long it will take.
And you never know whether it's useful.
Exactly.
So the ability to play with something.
Yes.
Igor, I mean, astronomers here running and of course managing these daily terabytes of data, they use such things like this Amazon, what do they call web services?
Cloud service.
To run.
It would be a sign of the enormous success of us all if we're using cloud. But I think that's a future step.
No,
it's not so
mean,
cloudy though. I think it's actually.
But I mean, what you're proposing is something like a modern version of what used to be called a quantum, maybe it's still a quantum chemistry program exchange. I mean, it's sort of like, here's all these codes sitting there, and you can use them, and they're installed on this machine, and they run on this machine. And maybe if you're lucky, they will also run on that machine and that machine as well. But
and so
that's a small step. But not.
It's good. If it's small, then it might happen.
Yes.
Right. If it's the first step has a big step, then it's not going to
And I
happen.
think that this bottom-up approach can, if it's a good idea, it grows exponentially. So then it's suddenly big. That's what I think.
I think it can be done. I'm not against it, but I don't